Hello everyone, welcome back to lesson 27 where we're talking about L'Hopital's rule and we're talking about the other indeterminate forms. Right now we have now learned four. We've learned 0 over 0 and infinity over infinity. These are our two classics. These are the ones that we learned at the beginning of the school year, and these are the ones that we've learned back in Calculus AB if you guys took that. In the last video we learned infinity minus infinity and then 0 times infinity. And students always ask, why these are also indeterminate forms. Well, infinity is, something that you cannot measure. It's an idea more so than an actual value. So infinity plus infinity is not one because that's infinity. Like that's just a huge freaking number. So infinity plus infinity is not an indeterminate form. However, infinity minus infinity cannot be zero. It's not zero. I use the analogy that you have 2 billionaires and you take the wealth of one of them and subtract the wealth of the other one, you're not going to always get zero, right? These are just two idea of numbers. The same thing with this right here, 0 times infinity. This is an idea. Students are like, well, it's always zero, but it can't be. It can't always be. Just like 0 over 0 is not zero, right? So we can't multiply something by something that we can't measure, even if it happens to be zero. So that's why we have our four indeterminate forms of what's going on here. Well, now we have these. We have 1 to infinity. We have, again, this is infinity. It's not a real number, so we just can't assume that this is 1. 0 to 0, 0 raised to 0 power is the same logic between 0 over 0, and then infinity raised to the 0 power. What we need to do for these properties, and notice that these are the ones to the exponents, is we're going to incorporate a natural log. So let's go ahead and get started with this problem down here below. Now, I'm going to show you guys 2 of these 3 in this video, but all 3 of them are done the exact same way. So we're going to start out with example number 6, where I'm going to plug in x approaches 0 from the right of sine of x raised to the x power. So this one, sine of x, is a function that we know looks like this. Right, this is our function for sine of x. So as x approaches 0 from the right, we're going to get 0. And if we plug in 0 to x, we're going to get 0. So we have 0 raised to the 0 power. And so that's going to be our indeterminate form for this. So what we're going to do is this. We're going to go ahead and write the limit as x approaches 0 from the right of sine of x raised to the x power. And we're going to go ahead and set that equal to y. And y is going to be the answer. We want this to be our answer for this problem. Now, students ask, do we have to write out the indeterminate forms for the exams? And the answer is no. I don't ever expect, anyone to be like, what's the indeterminate form that you have to know? It's that when you know what the indeterminate form is, you know what method to apply. Is usually what I tell students. For infinity minus infinity and 0 times infinity, you want to rewrite it as a form in terms of a rational function. And we're going to do that here too. But these other 3, we're going to add the natural log. So there's a property that we can use that we can employ the natural log inside of this limit. And then, again, what we do to the left, we do to the right. So there's a property here that we can learn that basically says that I can take the limit of x approaches 0 from the right of the natural log of sine x raised to the x. But again, we have to equal that to the natural log of y. I'm stressing this because when we find this limit, we're actually not finding the value of this one. We're finding the natural log of y. So let's do this now. One of the things that you guys can easily see that can happen now is we can move the x over, or move the x down, I should say. So x natural log of sine of x. This is how you would always, evaluate an exponential function. You can always just add the natural log or the log and move it down. And so we have x natural log of the sine of x equals the natural log of y. And I'm going to keep setting it equal to the natural log of y because I don't want us to lose the fact that this limit that we've now created is not the actual same value as the one that's right here. And so just like in the previous video, we're going to rewrite this. We're going to rewrite this as the natural log of sine all over x to the negative 1. And again, this is going to be equal to the natural log of y. So you always want to get it still in the indeterminate form of 0 over 0 or infinity over infinity. So we're going to do it like this. So the sine of 0 is going to be 0, the natural log of 0. Well, we can't do that. But again, we're looking at 0. And this is why we have to do 0 from the right, because this is actually going to end up being 0. So it's going to end up being 0 over 0. So that's why the 0 to the right here, because you can't take the natural log of the sine of x, because that would give you the natural log of 0, and you can't do that. But we can look at that graph from the right. So the sine of x, the natural log of sine of x over x to the -1 is 0 over 0. So we have to employ L'Hopital, which is not shocking to us at all. So we get the limit as x approaches 0 from the right. Well, the natural log, the derivative of the natural log of sine is going to be 1 over sine times cosine. And then this derivative is going to be -1 over x squared. And that's going to, again, equal to the natural log of y. You don't have to keep writing the natural log of y out. I'm just making sure that everyone's okay with that. All right, that we're doing it this way. And I'm going to rewrite this. I'm going to keep this in red because I just want to rewrite it as the limit as x approaches 0 from the right. And I'm going to go ahead and do -x squared cosine of x all over sine of x. And again, that's equal to the natural log of y. So I just rewrote it to get it into a true rational function. And so now I have this. If I plug in 0, I'm going to get 0 in the top. Sine of 0 is also 0. So I got 0 over 0. So I'm going to have to do it one more time. And we do. It's pretty straightforward. So we're going to do the product rule now. So we're going to do the first times the derivative of the second plus the second times the derivative of the first all over your denominator. Derivative of your denominator. I almost said the derivative square, but no, we're not doing the quotient rule here. We're doing the derivative of the top and the derivative of the bottom. If I plug in 0 to the top, again, I'm going to get 0. Now, when I'm going to set that equal to the natural log of y, we're going to get 0 on the top. We're going to get cosine of 0, which is 1. Right? Cosine of 0 is 1. So we're going to get 0 over 1. So I know that the natural log of y, is going to be equal to 0. So 0 is equal to the natural log of y. So what value is equal to, the natural log of what value is equal to 0? And this answer ends up being 1. Right? The natural log of 1 is equal to 0. So this limit is equal to 1. So when you have an indeterminate 1 to infinity, 0 to infinity, infinity to 0, you're going to do the natural log. You're going to rewrite this as a rational function, take the derivative, like you normally would in the top, take the derivative of your denominator, evaluate it. If you have to do it a second time, do it to the point where you're going to get some value. And then that value is equal to the natural log of y. Okay, so let's look at example number 7. And in example number 7, we're going to see what indeterminate form we have here. So we're going to go ahead and plug in infinity over root c and x. So we have 1 plus 2 over infinity. Well, any number over infinity is going to be 0, right? It's a bottom-heavy function. So I'm going to have 1 and then infinity in the x. So 1 to infinity. So our indeterminate form here is 1 to infinity. It is one of our 3. So we know to do what we did in the first example. We're going to take the limit as x approaches infinity. We're going to add the natural log. And guys, the reason why, and you already know this, you're BC students, so you know why I'm doing this. We can add the natural log because we want to be able to get this exponent down, right? And these are going to usually be variables like x or 3x or something really simple that we can just pull it down right here. And so this is going to be equal to the natural log of y. Now, I'm going to be a bad teacher here, and I'm going to leave the natural log of y. I'm going to keep this in my head that this is going to be equal to the natural log of y, and we're just going to solve this, and then we're going to come back and set it equal to the natural log of y. So I'm not going to write the natural log of y every single time for this particular example. So let's do it. Well, oops. I've already done, this particular part. But anyways, we're just going to find out what this is. So, and then we're going to set equal to the natural log of y. So I'm going to move the x down, and we're going to go ahead and do this. And I'm just going to keep going with it. We're going to do the limit as x approaches infinity. That's supposed to be approaches infinity. I don't know what that looks like. It's, so x approaches positive infinity. The natural log of 1 plus 2 over x all over x to the -1. So let's go ahead and rewrite that as 1 over x. Like, why not? Now remember, as we're doing these questions, we are remembering that this is equal to the natural log of y. It's equal to the natural log of y. So now we're going to take the derivative of the top, and notice that every time that I'm doing this, I'm keeping the integrity of my problem alive with the limit as x approaches what we're looking at. So the derivative of this is going to be 1 over 1 plus 2 over x times the derivative of this, right? And this is going to end up being the derivative -2 over x squared all over -1 over x squared. So just like in the previous example, we can eliminate our sign, our negative sign here. So this goes away. And the x squares are going to also cancel out. So we're going to continue on with this problem, and we're going to say that the limit as x approaches infinity is going to be 2 over 1 plus 2 over x. And we're going to plug in infinity. And this, again, is going to end up being 0. So this answer is going to be 2. Now remember, this 2 is equal to the natural log of y. So the natural log of y is equal to 2. Now you guys hopefully remember how I can solve this. We can rewrite this, and so this is the natural log of e to the y. So e squared is equal to y. So this is how you rewrite this, and I always call this our little heart method on what we can do for this problem. So we take the e, we raise it to the 2, and we set it equal to this y. So e squared is equal to y. So y is going to be equal to e squared. So this answer to this problem is going to be e squared. So concept is very similar to the example we did in number 6. They're almost the exact same thing. The structures are the same thing. We have a different function that we have. In this particular example, we had to do the product rule. So we had to find the second derivative. But, you know, for some of these examples, it's pretty straightforward of what you're going to see with these problems. So I hope that makes sense to you guys, and I think that's a good ending of this problem set. I will tell you again that we've just done 0 to infinity, or sorry, 0 to 0, and we've done 1 to the infinity. If you get infinity to 0, you do the exact same thing. You incorporate the natural log, you move it down, and you will be able to solve it pretty straightforward. So that's all I have for this lesson. I hope this made sense to you guys, and I will see you in the next video.